Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we're going to finish up our look at solutions. First, we're going to start out by talking about conversions between different types of concentrations, and then we'll finish up with a little discussion about solution suspensions, and in particular, colloids. Now, one of the things that you need to be able to do is to convert from one type of concentration to another if given the right information. And remember, we had four concentrations: percent or part per hundred, parts per million, parts per billion, and then molarity. And you do need to, if given the right information, be able to convert back and forth between these for my test or potentially the AP test. Now, you're going to start by understanding what the concentration really means. Now, I'm not talking about the equation, so to speak, but I am looking at what's related to the equation. So be careful when we talk about what it means with the ppH, ppm, and ppb. Really, we aren't looking at the whole equation. We're only looking at part of it. So for mass percent, let's say we've got 6% by mass. Well, what does that really mean? Well, remember, when we divided the part over whole and multiplied by 100, we would get 6%. So it would literally mean 6 per 100. So 6% would mean 6 grams of solute for every 100 grams of solution. And we would also then have 94 grams of solvent. So really, I've established for 100 grams of solution how much solute, solvent, and solution I had in as easy as method as possible. Now, the same thing is true with parts per million and parts per billion. And remember, these are also ratios just like above, but they're not per hundred, they're per million and per billion. And don't forget, mass percent is the same as ppH. So what does 6 ppm mean? Well, it means you have 6 grams of solute for every million grams of solution. And 6 parts per billion means you'd have 6 grams of solute for every billion grams of solution. Because in the context of this chapter, we were looking at all of these as mass ratios. And then literally, in each case, you would find the ratio, which is a per one number, and then multiply by 100, multiply by a million, or multiply by a billion. If you wanted to convert these to to use actual equations. So don't confuse what it means here. This is part of the equation, so to speak. And we can do the same thing for molarity. If we have 6 molar, what does that really mean? Well, it means we have 6 moles of solute for every 1 liter of solution. And don't forget, out of all of these, molarity is the only one that's temperature dependent, because your mass isn't going to change when you change your temperature, but your volume will. So when you're doing these concentration conversions, first step is always going to be to think about what the concentration they give you means. So to convert between any of these, start by writing what the concentration means. It may seem simple, but it is a very, very important critical step. So what you're going to do is literally what we did above for all these 6 amounts. Now, let's say we're converting between ppH, ppm, and ppb. This is a very different type of math than when we involve molarity. And this is actually a fundamental, easy type of math that most of you have done before. So first, we're going to write what it means. Remember, I said we always start with writing what it means. And then second, we're going to set up a proportion so that we can convert from one to the other. It really is that simple. So what is the part per million concentration of a 0.035% solution of NaCl? Well, you start by looking at what it means. Well, it's 0.035%. That means 0.035 grams of solute per 100 grams of solution. And what we're trying to do is we're trying to convert that into how many would be dissolved in a million, because this is ppm. So if we dissolve 0.035 in 100, how much can we dissolve in a million? Fundamentally, that's all we're doing is setting up this proportionality and solving for x. So in terms of ppm, this would be 350 parts per million. And remember, that actually is why we use ppm and ppb. When we're dealing with lower concentration things, we get more normal numbers for the general public. So fundamentally, going between the red ones, I guess it was the, if I jump back real quick here, going between any of these black concentrations, it's really just setting up proportions to do it. And that's all you're doing in the problem. Now, the one that's a little bit trickier, it's not hard, it's just a little bit more involved. You have to understand one more thing, basically. To convert back and forth between percents and molarities. Because remember, if we get to percent, we can get to any of them. But how do we convert back and forth between these two types of units? Well, first, you start by writing what it means. And then second, we're going to write the equation for the desired concentration. That's going to remind you of what we have and what we're trying to get to. Once again, it's an important step for making this as easy as possible. And then the third thing we're going to do is we're going to use molar mass to convert between our mass and moles. So if we knew the mass of the solute, we could get to moles of solute. If we knew the moles of solute, we could get to the mass of the solute. So molar mass is how we would convert with solute amounts. And then the other thing is volume and mass relationships. Well, that's where the density has to come in. So you'll notice every single time we're doing this type of concentration conversion, they always give us the density. And that's so we can bridge these two different types of unit, a volume and a mass. If they give us the density of the solution, and we know molarity is moles per liter, which remember is moles per 1,000 milliliters, we can establish a volume and a density and find out for that volume what would be the mass of the solution. So we're really just going to use the density equation for the other type of conversion we need to do. And then once we've got our amounts, we can actually solve, plug and chug. So what is the percent by mass, which is ppH, of a 1.35 molar solution of NaCl? The density of the solution is 1.05 grams per milliliter. So notice they've given us, in this case, the density. That's kind of a dead giveaway. You're going to be doing this type of problem. Now you start by writing what it means. Remember, 1.35 molar is 1.35 moles of solute, which in this case is NaCl, per 1 liter of solution. So to start with as easy as numbers as possible, we're going to assume we have a liter of solution, and then I would know I have 1.35 moles of solute. Now, my target is percent by mass. Well, that's the mass of the solute over the grams of the solution times 100. That would give us the percent by mass. So that's what I've got. That's what I'm trying to get. So you can see what we're really doing here is changing two things. One, we've got moles of solute, and we really need grams of solute for this equation. How do we go about doing that? Well, that's just a straight molar mass conversion, like you've done hundreds and hundreds and hundreds of times in the last 2 years of chemistry. And then two, we need to convert liters of solution to grams of solution. How do we go about doing that? That's the density relationship. And remember, the molarity is moles per liter, that's 1,000 milliliters. So to simplify the math here, because the density is grams per milliliter, I'm not going to use 1 liter, I'm going to use 1,000 milliliters. So it's 1.05 grams per milliliter equals X over 1,000 milliliters. X, which would equal the mass of the solution, then has to be 1,050. And remember that per 1 liter in this relationship would be considered an exact number. So that's exactly 1,000 milliliters. So it would limit us to 3 sig figs here. And at that point, we just plug those things in and calculate. It would be a 7.52% solution. So that's the last thing I want you to do from this section of the book. It's to do the conversions between the different types of concentrations that we deal with. Now, the very last section of the chapter gets into colloids, but I want to make it more of a general overview of our 3 types of mixtures, some heterogeneous, some homogeneous, suspensions, colloids, and solutions. Now remember, suspensions of particles larger than individual ions or molecules. So things that haven't broken down to a individual molecule or ion, but a clumping or an aggregate of things, but that's still very, very small. It's not going to settle out by gravity. In other words, the motions of the solvent particles are going to keep them stirred up, even though you would think they shouldn't. And that's what a colloid is. It's like a form of suspension, but it looks like a solution. So it's kind of a tricky thing. Suspensions are much easier. If you've got very large particles that separate out, then you've got a suspension. Now, there are lots of different types of colloids in everyday usage because they're incredibly important, because nobody wants to drink chunky milk. They don't want their milk to separate. So when we make and use paints, we don't want to have to always stir it if possible, because colloidal dispersions stay mixed up enough that we don't need to stir those types of things. And that's really useful in a lot of commercial situations. So there's many, many different types of colloidal dispersions, and you can see a list of them from the book here. Now, if colloidal things look like solutions but are actually more like suspensions, heterogeneous mixtures, how do we actually tell them apart? Well, one of the easiest ways is with the Tyndall effect. When you pass light through a solution, if you don't see the light beam, then what you have is a solution. The particles are so small they don't visibly scatter light. But that intense beam of light, if it's hitting bigger particles, like suspended particles or colloidal particles, even smaller particles, then it is large enough to actually scatter the light. So to the naked eye, many of these things look cloudy. And you can see here in the forest, because of the particulates, the solid particles that are stirred up in the air inside the forest, you can actually see the beams of sunlight going through the air. That means that air must be a colloidal mix. So anytime you can see the beam of light, then it's a positive tyndall. If you can't see the beam of light, it would be a negative tyndall, and therefore you have a solution. So to put together our three types of mixtures here, suspension, colloids, and solution, there's a variety of things you should understand to differentiate them. First of all, do they settle out? If they do, it's a suspension. Colloids and solutions would not settle out. You don't have to stir them up to keep them mixed. Now next, particle size. Suspensions are the large particles, solutions are the small particles, and intermediate in between the two would be our colloidal particles. And if our colloid particles aggregate too much, it goes from a colloid to a suspension, and we no longer have a colloid, and it will separate out. And one of the easiest ways to detect and differentiate these from solutions is using intense light and the Tyndall effect. Both suspensions and colloids would have a positive Tyndall, but a solution would not. And then fundamentally, the last thing you should understand is how they're similar and different in terms of types of mixtures. We have heterogeneous and homogeneous mixtures. Suspensions and colloids are actually heterogeneous mixtures, and solutions are homogeneous mixtures. And in industry, for commercially sold products, making it colloidal makes it more homogeneous, and then the consumer doesn't need to stir it up. So colloidal mixes are very useful commercially. Now, they're also very useful in body chemistry type situations. Some biomolecules that are very large, so we often refer to these as biological systems because there's these big molecules, and sometimes they can be aggregates of these big molecules. In other words, the molecules clumping together. These large molecules, and we've looked at this with solubility, can have polar and nonpolar parts. And that complicates things a little bit. Which one is dominating is very important in terms of how the molecule is going to behave and how soluble it is in polar and nonpolar substances. Now, the water-loving part, the polar parts, the hydrogen bonding parts as well, on certain types of large biomolecules would be our hydrophilic, our water-loving parts. And then we have the nonpolar, typically a hydrocarbon, water-hating ends. In this case, our hydrophobic parts are folded in and our hydrophilic parts are exposed on the outside, making this thing much more likely to interact with water. So in this particular molecule, our hydrophilic parts on the surface make this thing much more soluble in water. And what can actually happen here if we get a biomolecule that's like this is we have a hydrophilic colloid. So the parts that become attracted to water are exposed on the outside. And with proteins and things folding in different ways, sometimes things can go from hydrophobic to hydrophilic depending on the solution that it's in and its concentration and other variables. Now, hydrophobic colloids, when we have nonpolar things, how can we actually keep them in colloidal form? Because most nonpolar things are going to separate into a heterogeneous mixture, a suspension. And that's because the water molecules that they're in are strongly attracted to each other. And those nonpolar molecules are not very strongly attracted to the water. So the water molecules are going to stick together. And that's going to leave our nonpolar parts to stick together and aggregate. And our colloidal stuff that we have when we shake it really, really hard into small particles is quickly going to aggregate and become a non-colloid. It's going to become a suspension. Well, how do we keep those small particles from aggregating? Well, two ways your book talks about would be these two methods. Now, the first is adsorption. Don't confuse this with absorb. We're not taking it into the inside. It's adsorbing it, sticking it to the surface. So if we end up with negative ions adsorbed to the surface of our nonpolar substance, then what's going to happen is we end up with a small colloidal particle that's not going to aggregate, because when these two particles get close together, they're not going to combine, they're going to repel each other. And they'll surface charge make this thing more attracted to water molecules. So this is one method. The ions stabilize the colloid and allow it to stay in its non-aggregated form. So it's going to prevent it from clumping into a non-polar suspension. And what we end up doing here is really use ion repulsion. So that's one method, is adsorption. Another method for keeping things colloidal would be basically what soap does. And what soap is, it's an example of an emulsifying agent. Soaps or emulsifying agents typically have a large nonpolar and a polar part. So they have a hydrophobic and a hydrophilic end. In this case, it's C double bond O. It's just missing that H. So this comes from Cu. So this would have been a weak acid basically in solution. And when that portion forms, we now have a polar and a nonpolar part. The nonpolar part can stick to and attract to the nonpolar droplet, but the polar part is not going to be attracted. And what we end up with is, again, a surface charge. As our nonpolar part gets exposed to the outside world, when these two drops get close together, they're going to repel each other. So charge repulsion of like ions or like charge is going to keep these things from aggregating. So that's a hydrophobic, or methods of keeping hydrophobic substances colloidal. And that finishes our chapter 13 notes.